right, for delivering a session on a very recent advanced topic of computer vision known as 3D human perception from vision to robotics. You will see, I think probably he's with Max Planck Institute, Germany. He's currently a final year PhD candidate. He's also working in Meta Reality Labs juries as a research scientist. His research focuses on understanding human motion and interaction. Probably his lab is one of the very popular lab, if I'm not wrong, who's currently focusing on this particular topic. So before his PhD, he spent 4 years in industry at Intel and Mercedes-Benz, where he developed human pose estimation models that were deployed in real-world systems. He has also published several papers in top-tier conferences such as CVPR, ICCB, and so many others. So now I request Sai Kumar Dwivedi to start the session.
Thank you, Dr. Deepak, for the warm introduction. I am Sai Kumar Dwivedi, and today I will talk about 3D human perception from vision to robotics. Feel free to stop me if you have any questions. I also would have questions in the end, and we'll discuss about it. So before diving into this topic, I have been working on human perception for a long time, and as was mentioned, I worked in industry for 4 years, and in that, I specifically worked in Mercedes-Benz, where I worked on deploying head pose estimation models that got deployed in the car, and I'm going to show you some demo from that model. This is MKBHD, you probably know, is a famous YouTuber. He reviewed a car where there is a camera inside the car, and you can basically estimate the head pose, and you can control the mirrors based on your head pose. Similarly, using the same algorithm, you can also control, let's say if you turn back, your sunrise goes down, right? So it basically recognizes the head pose, and some feature in the car get deployed. During this time, I decided that I would want to do research full time, and this is why I thought I would do a PhD. But when I questioned about what I would work on, right, in my PhD, and that gave me this picture of this famous movie I'm going to show you, and that also ultimately said, what is the ultimate goal of an AI, right? So I'm just going to show you a video of Ex Machina. You probably would have seen this movie in 2014. This is for those who have not seen this movie. The lady is a robot, which looks like a human, which acts like a human and behaves like a human, and then the protagonist attacks the human, right? But obviously, we do not want robots attacking us. But what is the ultimate goal for a human? And I define it in 3 ways, right? I say that AI that can reason like a human, right? That can looks like a human and acts like a human. This would be the ultimate goal of a AI, right? And where are we in this picture, right? So coming back to the point that where are we? I mean, we see so many advances in AI recently, and then we would want to look into various aspects of this. So if you look about this, right? The AI that reasons like a human, you probably pretty much are very aware of it. There are many LLM model like ChatGPT, Grok, Gemini, you name it, right? Like there are so many that reason like human, that talk like human, and that is very difficult to differentiate real versus virtual human. And and we have already seen that it has passed the Turing test. So it is no longer a great, I mean, you can always debate about saying how good these models are, but these are pretty good. I mean, you would not be able to differentiate between human and a virtual one. Okay, now coming back to how looks like a human, like do we have systems that look like a human? And I'm again gonna show you a movie. This is a curious case of Benjamin Button. You see Brad Pitt is enacting an older character. So for example, if you see him, he's much younger, but in the movie, you see an older version of Brad Pitt, and we have amazing techniques that can basically recast your face into an old looking one. So I can always say that, oh, okay, this looks very much real like a human, right? And we also have another movie, Ward WZ, which also enacts, crowd scenes. For example, these are not real humans, but you see these humans created in the virtual graphic scene. But you can always argue that, well, these has not been AI, this has been manually created. There are so many tons of artists and computer graphics engineers who sit on this, curate each of these frames, and then edit all of these frames to make it realistic. But I'm going to show you a paper called Dream Human from our colleagues, Kolosotro from Neurist 2023, where given a text, we can basically generate humans that looks real. Well, we can always argue that these are not really great, but we are there, right? This might not be of great quality, but in research, we are still there. But we have enough technology that given engineer, we can basically create a model that looks like a human. But when it comes to acting like a human, I think we are very, very far away, right? So if you see this movie called Gravity, which is in 2023, everything is, if you look at the movie, everything is computer graphics, right? But the only thing that has not been done is basically the motion of a human, right? And this is very, very difficult. Like if you see the Avatar 2, same case, right? So everything is graphics except the human motion. So why is human motion very difficult to do? Even you have so many artists, even you have tons of graphics engineer, why are we not able to model human motion? And I think this part really intrigued me into understanding how do you model human motion, because and this comes to the question, like, why is it hard to act like a human, right? We have done a tremendous amount of research on reasoning like a human. We have done tremendous amount of research on looking like a human, but acting like a human is really, really difficult. And that is primarily because body has like 600 plus muscles, like 200 plus bones, many, many joints. And we move in a complex motion, which is very hard to simulate in a physics engine. What it means is that there is a fluid nature of our human motion, which is very difficult to do. And before going back to taking an AI to basically solve this, let's define the representation. So the way that we define representation for a human, right? So we define this as a 3D points. So let's say this looks like a human, which has 6890 3D points, and which is characterized by something called a simple model, which is from our lab in Germany, where imagine this as a black box, right? So simple model is a black box, which is controlled by this 82 numbers, right? 72 numbers for pose and 10 numbers for shape. So given any random numbers, you can generate a human which looks like the one I'm going to show you in the next slide, right? So the characterization of this human is like you have these vertices, which we talked about earlier, the 6890 vertices. We have something called joint location, which is basically the joint location like a really human would. And then we have this blend shape. So imagine blend shape as something where each vertices is basically controlled by how the joints move. And there are these pose parameters, which basically helps us to move. And what it looks like is this 3D human model, which can do any kind of pose, right? So this is a generative model which can do any kind of pose, and also can do any kind of, for example, it can do any kind of body shape. So for example, it can do any kind of pose for different body shape. And we keep this as a basic representation of representing human, because we still need some parameterized form to represent human, because imagine there are so many nuances to different body shape, different body pose, and we want to build a system that can predict these parameters to define a human, right? So now the question is, where do you get data for training? So unlike other classes of vision problems like classification or segmentation, this 3D human data is very difficult to get, because we have something like called a capture hall, which we have in the lab in Germany, where, as you see, this is like a typical Hollywood studio where people wear gloves. So, and these are called markers, right? Where you put, these are IR markers, and there is camera, as you can see, there are cameras here, and it captures the human motion doing in different poses. And then we basically convert this sparse marking points to 3D mesh. And that's how we collect the data. We also have something called an IMA sensor, which basically means this is think of this as a wristband. As you can see here in this part, where the person is wearing some kind of wristband on the legs and feet, and once you move, it basically tracks where the body moves, and you collect data from that. But we can always say that these are not enough data, right? Because you can only do so much in a limited lab setting, and you can only wear I mean, you cannot really wear these bands everywhere because this needs to be calibrated, and also you have to be careful about not exposing this material to something really bad. So this is very difficult. So what people have ended up doing is that people used have like something called a joint reprojection loss. So think of this as a 2D human pose estimation task, right? So instead of a 3D, so let's say you have a 2D human pose estimation. And what people do is people take this 3D human pose, you have a camera projection matrix, and you basically reproject the 3D into 2D, and then you define a loss based on these 2D key points. And that's how people have been able to scale up, right? Because you can only do so much in the lab, and but the obvious problem is that this is not enough, right? Because as you can see in this problem, you have, let's say, a 2D pose, and this 2D pose can be represented both by this 3D and this 3D, right? Because when you're projecting, you are basically you are ignoring one Z vertex, and which means that everything that projects to that plane gets merged to a 2D pose. This is a classic camera projection problem, right? So you cannot really rely on the 2D key points. And what a typical model looks like in a 3D human pose estimation, like if I have to define it from a, in a way of, let's say, image classification task. So you have an image which goes into an encoder, which is basically think of this as some kind of a backbone, and you have some regression model which gives you this pose parameter that we talked about in the earlier slides, right? So we are representing this 3D human by this 72 numbers. So all the neural network has to do is predict the 72 numbers. And for shape, you have to predict this 10 numbers, and you have to predict some kind of a camera that you can use all the 2D key points, because, well, that's the only thing that you have for in the wild. And all the variety of the work that has been done. So this is a 2018 work. This was one of the first work that estimated humans from a single image, right? And as we said in the beginning, that acting like a human is very difficult, and we are trying to build a machine learning system that can do that, from a data-driven way. And if you see, the biggest problem for human understanding has been this diverse, high-quality data, and all the papers that you can see has been around this, right? So, like, how can we collect high-quality data, or if not, how can we leverage this data that we see in the world, and how can you use it? And this comes to my first paper in my PhD, which is basically DSR, which is called differentiable semantic rendering, and this is in ICCV 2021. And the idea is very simple here, right? So the goal is that given a monocular RGB image, we want to estimate the 3D human model, right? And we want it to be as accurate as possible. And as we saw in the previous slides, that it is really difficult to use key points, because key points do not supervise body shape, right? Because let's say you have a joint, and this joint, I mean, for example, for a person with a high BMI or a person with a low BMI, the joints would be same, and you would not be able to supervise with a body shape. But if you use segmentation, which is also a 2D segmentation that you see in the wild, they don't really match the projected simple body. What it means is that, as you can see from the previous representation that we talked about, like simple, this is a naked human body, right? Which means that it doesn't have clothing. And if you take segmentation, which would have the clothing part, they would not match, right? Because you will not be able to put an MSE loss on that. And the idea was that we can use like some high level semantics, and we can differentiate between clothing and non-clothing, and then use it to supervise this model. So the high level idea of this paper was, given an input image, we take an off-the-shelf clothing segmentation model. So all of these colors represent different part of the human body. For example, orange represents the upper part of the body, green represents the lower part of the body, and different colors of hands represent different colors. And what we do is we take this minimal clothing and we take this segmentation map, which we use an off-the-shelf method for, and we differentiate between minimal clothing and clothing. And the idea was that we built a simple model with a semantic prior, which means that we have a probability of defining which vertices belong to which part, and we just do semantic rendering loss. I'm not going to go into detail about that, but what I'm trying to show you here is that when the community realized that there is not enough data that they can use to leverage it, people came up with various different ways can leveraging like some weakly supervised data. For example, here like people have used key points, people have used segmentation, which doesn't really work. So here what I did was I used a clothing segmentation, which basically differentiates between clothing and non-clothing part, because the idea was that if you take a minimal clothing part, the hands part, this would perfectly align with the body, right? But the clothing part, not so much. By differentiating that, you will be able to leverage it. And you see that there's a very common pattern in all of the work is how do you leverage all of this data? How do you leverage collecting high quality data or using the data that is available, right? And here are some results. On the left, you see EFT, which is the baseline method that we used in 2020, and this is a DSR, which is ICC 2021. And you can see the colors, and this perfectly matches the silhouette of a human. And same goes out here, right? So you can see, I mean, it's not perfect, but it's better than the baseline that we had. And this basically using the semantic rendering loss really helped us. If you're more curious about what exactly is the semantic rendering loss, because it'll be too much to cover in this short session, I do advise you to go look into the paper. It's a very interesting concept of how do you use rendering as a loss to define the 3D body. Okay, now coming back to the next problem, right? So we talked about this problem where we said that people used all kind of different weak signals, right? So that includes segmentation, key points, and whatnot, right? But then we started seeing a very common problem, which is called a mismatch between 2D and 3D, right? So remember this thing that I talked about earlier, that your 2D can really mean, so this is a one-to-many mapping, right? So a single 2D input can basically mean multiple 2D outputs. And what happened, by using so much of pseudo ground truth, which we call as the ground truth that is derived from these weak signals, right? What really happened is that it perfectly aligns in the 2D, right? But when you see in 3D, the legs seem to be bent, right? So there is a mismatch between the 2D and 3D. And more people relied on this 2D information, the worse and worse it got, right? And you see these artifacts. So we call this as an artifact where the 3D doesn't really align with the 2D. And we wanted to build a model which kind of generalizes in the wild, but we do not want to drop without a drop in 3D accuracy, right? Because 3D is very important to us, and we wanted to, and I'll show you why we are talking about 3D, why not 2D in the later part. So if you see the core of the problem was that we had like the assumption in the community was that we used a very simplified camera model. What does mean by simplified camera model is that if you remember the camera model modeling in your computer vision courses, you see that there is something called a pinhole camera so all of these modelings were done on the pinhole camera where the focal length was assumed to be fixed, because we really didn't have a focal length that you do, right? So what people do for estimating these models is that people assumed a focal pinhole camera with a fixed focal length, right? Which is not really the case, because these are images taken in the wild. So the assumption of the focal minimal, like the fixed focal length, doesn't really seem valid. And because of that, you see these artifacts, because when you change the focal length, the model has to like fit in, right? Because it has to still squeeze in the 3D body into the 2D, and this is where the problem starts. And the problem manifests in two phases, right? So when you're creating this data, like this biased pseudo ground truth data, here you're using a simplified camera, and when you're also defining a loss, you're also using a simplified camera. And estimating the camera itself is a ill-posed problem, right? Because how do you estimate camera from an in the wild image, right? This itself is a problem. So we thought, well, we can be something smart about it, right? So what we also analyzed is that, like, how bad is this problem, right? So, well, we said that camera is really bad, but how bad the camera can be. So we did an experiment where we said that keeping the 2D alignment, how much can 3D vary, right? So imagine this as a 2D rendering of the 3D, right? And this is again the 2D rendering of the 3D. I guess you can see my cursor, right? So if you see both of these, this looks very similar, right, in 2D. But when you see in 3D, these are very different. So keeping the same 2D alignment, the 3D can vary a lot. And when we are not really careful about it, it can cause these artifacts where the legs and the body starts bending, right? So then we came up with something called a Tals loss. What does it mean? If you look on the left, what previous methods defined is that is a general trade-off, right? So we decided that these 2D data sets are really helpful because, again, as I talked about before, 3D data sets are very sparse in number, so we only have very limited 3D data. So people relied on this 2D data. But if you don't use this 2D data, it leads to poor generalization, right? We want a system that can generalize really well. But if you use it, then it causes this bias. So that's where we come with a very simple formulation where this is called a threshold adaptive loss scaling, where we say that if the loss goes beyond the threshold, we basically penalize it, right? So we penalize with an alpha, and we do it both for the pose parameters and also for the 2D joints. But there is an inherent problem, right? So what we are saying is that if the loss goes beyond a threshold, we basically scale it down, right? This is probably like 10 to the power minus 3 or minus 4. So what we're effectively doing is that we are reducing the learning for when the loss gets better and better, right? And then, well, it can definitely avoid your bias, but again, it creates another problem, right? So then you're basically stopping your model to learn beyond this loss scale. So what we thought is that, well, how can we basically leverage this prior, right? So we have this amazing prior that we have in the lab data, right? But which is not in the wild data. So the thought that we could use some kind of prior, right? But if you think about like Gaussian mixture model or a variational autoencoder, these are very biased towards frequently occurring poses, because if you remember the scale divergence loss, what it does is it basically pushes the latent to be closer to the unit variance, right? Which basically means is that you only have a very limited distribution. So what we ended up doing is that we defined a VQVAE over the pose parameters. And the advantage of a VQVAE is that this has no bias in the prediction, right? So what it means is that it inherently stops, it doesn't use any prior to define the distribution, right? So if you remember, so VQVA is a very commonly used very commonly used representation in LLMs and all kind of large models now. And one of the effectiveness of that is that it doesn't have a prior, right? So what you do is you send and pose parameter. So this is the 72 numbers. Remember the 72 numbers I talked about earlier. You send in a pose parameter and then you get the pose back, right? And you have an encoder and a decoder and a code book, which basically discretizes the pose parameters into a valid code book, right? And again, unlike the Gaussian mixture model or a VAE, it doesn't have a prior. And because of the not, what it ends up happening is that you can basically leverage any kind of pose that you have seen. So not necessarily the common part, right? And what we did is in the first stage, we trained this pose VQVAE, which is a distribution of the pose parameters without any kind of prior. And what we ended up doing is that we took this decoder and keep it frozen. So this is the overall architecture of the estimation. So given an image, we have some backbone which basically extracts the features. We have a transformer block which estimates the pose, shape, and camera. And what it does is that it does give you pose vectors. And what it happens is that it goes into this decoder which is frozen, right? Remember that we in the first stage, we first trained this pose encoder and decoder, and we keep the decoder frozen. And what it ends up happening is that because this decoder is trained on very high quality data, the output of the model will always be high quality. And remember, this is a very general recipe that when you have noisy data, right, and you can use this as a way to regularizing your model, right? So you have this let's say, imagine that you have an unpaired data where you have very high quality data, but you do not have anything that combines with some kind of an image or some kind of other input modality that you are looking into. So in the first stage, you can train a model that basically does this kind of a representation learning, right, without having any kind of prior. And what you end up doing is that you can take this decoder, keep it frozen, and then plug it into a network basically that predicts this output. And because this is trained on high quality data, your output will always be high quality. And if you see, I'm going to show you the results because that's more important than some bold numbers. I mean, we got way better numbers. So MVE is mean vertex error. So the lower the better, right? So the lowest number is the better, and we get way better than the previous model. But what is more interesting is this result, what I'm going to show you. Here, the color doesn't represent anything. The color just represents a different body because we have multiple people. And what we do is we estimate the 3D human pose, we project it on the video, and that's what you see as a result, right? And we can basically do pose estimation, like 3D pose estimation, even in this challenging poses where you're doing all kind of parking method, like all kind of, it's still not perfect, right? We are still not there yet, but it's the best that we can come up with the data that we have, because again, data is very, very limited, and this has been like, this works in the wild, right? And the small jitter that you see is because it's a per frame method, and what it basically does is it like stitches the per frame method into a video method, and there has been no temporal smoothing done of any kind in this method, right? And we do like, I mean, we get really amazing results. Seeing this, I mean, we get very good body shape, we get very good body pose, and obviously there are still rooms for improvement, but the perception for humans from an image and video is really good. Okay, now that we can do pose estimation, like 3D pose estimation from images and videos, okay, what about can we control this? And this is a paper from our colleague in CVP 2024, where called STMC, where given an like text label, we can basically control how the body moves, right? For example, if you see, okay, so let's go from the beginning. So you say that walking in a circle clockwise, and then you say waving in the hand, and this is kind of a basically directing it how to behave, right? So jumping, walking backwards and applaud, and turning 180 degree, raising hands, so it can do all sort of things, right? So we go from basically perceiving humans from images and videos to basically controlling it. But you see that there is a slight problem, right? So till now, what you have done in perception is basically humans alone, right? But humans in general do not occur alone, right? So humans always interact with an object in a scene, but all we are doing here is basically humans interacting alone, right? So as if, if you can see, there is a very, very weird pose that would come up here where the person is trying to sit, but then there is nothing to sit down, right? So you see, and the end of this in this part, you would see that there is a sitting down pose, but then that there is no chair, right? And we want to avoid that. Okay, so this comes to the next part of my paper, which is called Interact VLM. This was in CVPI 2025, and here the goal was, we don't want to just predict the humans, we also want to predict the objects, right? Because humans come with objects. So the goal was, given any in the wild image, we want to reconstruct the humans and objects in 3D, right? And we do so by coming up with an auxiliary task called contact prediction, right? So contacts are defined as touching points of a human and object, which is represented by the black patches, red patches here. So we want to do a contact prediction on the humans and also on the objects. And in that way, we can basically put them all together. You can always say that, why do we need contacts? Like, why do we define contact and what does it help? So what contact helps is that once you know where the humans and the objects touch, you can basically ground it, right? For example, we can define an optimization method that can ground the human, like for example, that can ground the human and object and bring them together, right? So what we did was we took the problem of joint reconstruction of human and object. So by the way, this is just to clarify, this task Okay, so this task is called joint reconstruction, and we do so by estimating contact. Now the question is how are contact labels created, right? So as I told you, these are collected in the lab, which is a very limited setting, right? We have this lab where there are cameras, and then basically we collect humans interacting with different objects. Or we have this something called a manual labeling, where you have a mesh painting tool, right? Where you take a 3D mesh and you basically paint there where the humans are in contacting the body. And what is the problem is that because these contacts are defined from a mocap, this is very limited to lab setup, right? And very expensive and very hard to scale. And again, if you take the contacts from manual labeling, these are again very tedious, very expensive, and very hard to scale. Right? Imagine how many different objects we interact with, and if you want to model all of that, collecting in a lab for all varieties of data would be really, really difficult to do that, right? And also we contact with multiple objects in real life, right? So we are eating with a pizza, we are sitting on a sofa, putting our hands there, right? We're not talking on a phone, sitting on a chair. Like we do all sorts of multi-object interaction, right? And because of this limited data, what previous method have done is that define contact as a binary task, right? So there is no segregation between contact with a chair versus contact with with a mobile, right? And this limits the task very much, right? So what we wanted to define is that we wanted to define contact for different kinds of objects. So if we wanted to model it in a different way. And so again, so we have two kind of problems, right? So first, we don't have enough data, right? Because data is very limited. Second is that even if we have that limited data, we will never be able to model such variety of different interaction we interact with, like with multiple objects, right? So again, so limited data, and we also want to reason about multi-object interaction. And so the idea was that can we use a foundational model with a limited 3D data? Can we do that? And that's where the interact VLM is basically defined, that we use a foundational model with the limited data that we have to basically build a system that you can do. So the idea was that given an RGB image and a query, we ask a visual language model, right, to basically use it. But then there's a problem, right, because we cannot really use a visual language model because the foundational models operate in 2D, right, while contact is basically a 3D. So we cannot directly ask a visual language model to say, oh, give me the contact in 3D, because they don't really understand 3D. Well, there is always an argument saying, do they understand physics or not? But then that's a different discussion. I can take it up later. But it's essentially what it basically ends up doing is that it doesn't really understand 3D. It has a notion of 3D. It has a notion of what looks like a 3D, but it really cannot define 3D in a proper metric form, right? So what we ended up doing is that we came up with this framework called RLL, which is basically a render, localize, and lift. So the basic idea behind this is that, well, language models and vision language models, they are pretty good in the domain that they are, right? But if you're talking about a 3D domain, which is not their domain, it is very difficult for them to learn this, right? If you ask them about reasoning, and you probably would have seen lots of papers coming up saying, oh, these visual language models are not very good at physics modeling and all. And that's true, right? Because they have not been trained to do physics modeling or understanding of 3D. The only objective of this large language models is to basically model what looks like a realistic one. And you could have very realistic one. For example, if you probably would have seen these examples of human interacting with something, and then you have this 6-finger, right, which is a very pretty common problem in the vision language model. So here the crux of the idea was that can we bring this our problem into the domain that they do understand, right? And what do they understand? They do understand 2D. They don't really understand 3D. So the idea was that can we bring this 3D problem to a 2D problem, right? So if you can convert this 3D localization of a contact prediction to a 2D localization of a contact prediction, then this will solve this problem, right? So that's the crux of the idea. So the idea was that we take a 3D human body, for example, here, simple the case, the representation that we talked about earlier, we render multiple views of it, right? And we do a 2D localization of it. We are using a multi-view localization. And because we know the camera which is used to render this, we can lift it back to 3D. So the idea is that we render the 3D, we do all kind of reasoning in 2D, right? And once you're done in 2D, so for example, what do you mean by reasoning in 2D is that you estimate the contact here, which you see as a small white patch. This is a 2D contact segmentation, and you do it per multi-view, right? So multi-view is basically you have a camera and then you take a 360 view of the 3D, right? And then you lift it back to 3D. So here is the architecture. I'll go in big details about it. So this is a typical image that is sent with a text prompt. We trained with using Lava, which is a VLM model, which is an open source model. It's pretty small. It's not that big. It's around 25, 30 GB of a model. And we fine tune is using LoRa, right? And think of this as a black box, which basically estimates some kind of embedding for humans and objects, right? So when we define a projection layer, which these VLMs can basically convert this language embeddings to any kind of downstream embedding that you want to train on. And that's why we use LoRa to define it. Okay, so, and what this model basically gives you is something called contact reasoning token. So think of this as you give an image and you query saying, oh, where do I see contact in this image, right? And this gives you some kind of tokens, and we have to convert these tokens into 3D. And this is where our framework comes in, where we say this is a render, localize, and lift. What does it mean is we take a human and an object, like both are in 3D, which is basically displayed here as a render of a 2D, and we take n views. So we do a multi-view rendering, like 360 view with some camera parameters, and we define multiple views. And what we do is that we pass it to a shared encoder. So this encoder is basically a SAM, this is a semantic anything model. We use this as a frozen network for the encoder part, but we train the decoder, right? So we have two different decoders for humans and objects, and we define contact for all of them. And because we know the camera which is used to render this, right? So we can basically lift it back to 3D, right? Because we know the exact camera metrics that helps us to render this. And basically we can triangulate this 2D points and then we project it back to 3D. But then there is an inherent problem, right? So what you are basically essentially doing is that we are giving a single view image, which is an RGB, which is an in the wild image, and we're asking it to do a multi-view segmentation, which is again a problematic because we only have a single view. So and this is the problem, right? So we are giving a single condition, we're asking it to do a multi-view segmentation. And again, there is no 3D consistency between this, right? So we are treating this as independent 3D view segmentation, which should not be the case. So what we do is we introduce a feature which is called a feature lifting layer, which projects this single view camera tokens to multi-view camera tokens, right? So it gets an embedding of human and object, and it converts it into a 3D embedding on that using the camera parameters. And to improve consistency in multi-view, what we do is we penalize using a 3D ground truth, right? So we take the 3D ground truth, which is in 3D, we backpropagate the loss from there, and then that's how we maintain 3D consistency. Okay, so here are some results, and like these are some numbers where F1, like the higher the better, and we beat the state of the art by a huge margin. This is like 25 F1 score, which is great because, well, the previous models didn't leverage the foundational model, and they only train in the very small data, and which really doesn't really generalize, right? F1 of 55 is really bad for a task. Okay, so what we do is, like, here are some results. So given an image, we query saying, can you estimate the contact with respect to the bed and with respect to the laptop, right? And it gives you contact, which is vertically depicted in red here. And you see contact predicted for the bed and for laptop independently. Here is one more example, a person carrying an umbrella. This is the contact with respect to the handbag, and you contact with respect to umbrella, right? So you can see, we are able to estimate contacts based on different body types, different objects. Again, same here, like fork and knife, right? So we see the left hand being properly identified and the right hand being properly identified, right? So we are able to differentiate between different, and the input is just a single image, right? So input is a single image, and we want to estimate based on that. Here, more example. Again, cell phone and handbag, and you see the context being predicted for that. Here are some more examples with the previous method, and you can see if you take this example, because this has been trained on very limited data, it gives a lots of false positive, whereas our model gives very good estimation of contact. And okay, so one of the things that we realized is that a very interesting fact that we did an experiment on was, well, we are leveraging this foundation model, right? And the whole idea was that the data is always limited, and we wanted to come up with a clever solution of how do you use less data, because again, 3D data is very sparsely available. So what we did was an experiment where this x-axis is the percentage of training data, and y-axis is an F1 score. And this orange bar is basically the method that is trained with 100% of data. And what we saw is that when a method is trained with a VLM, with only 5% of data, we're already beating the state of the art, right? And this is a very promising result because, well, interaction data will be very hard to collect, right? Because we will never be able to scale up to the different varieties of humans, a different variety of interaction that we do with different objects. So we somehow need a different way of tackling this problem, and using a foundational model will always be, always be great because it does have some understanding of our 3D world. But the trick was basically, I mean, if you want to summarize this paper in a single line, the idea was that the foundational models, they know a lot about our 3D world, but not in the modality we want them to know, right? So they do have some implicit understanding of it. So the best way to leverage this is that if we can bring in, if we can convert our problem, 3D problem, into a 2D problem, right, which is basically what they're expert in, we can really leverage this gap and take full advantage of these models. And again, this bits the takeaway is the baseline method with only 5% of training data. So what we ended up doing is that we taken in the wild image, we estimate this human pose estimation as we saw in the previous projects, right? We have an human pose estimation method, and we have something called a object retrieval, which gives you a 3D object given an image. And we use this interact VLM to predict the contact for both humans and objects. And we define a pose estimation method that puts them both together. And here are some results comparing with the baseline method and our method, right? So we are able to, so given just this single model, we're able to recover the humans and objects both in 3D, where it adheres to the 3D spatial positioning of both 3D and there. And here are more examples where you can see that the humans and objects kind of align with what you see in the 3D image. So imagine the potential of this, right? So you give an random image of you sitting on a chair, and we will be able to reconstruct the whole human and an object in 3D, right? Not in 3D. And here are more examples with different variety of objects, different kind of poses, right? And here are more examples with that, right? So now the question is, like, these are static images, right? But humans do interact with an object, but they want to also move it, right? Like humans never grasp an object and sit there, right? So I'm going to show you an method from our colleagues. This is called choice, which was an ECCV, which takes in this model and basically moves this model, right? Like for example, in a 3D scene where you can take a model, like take a human, take an object, given an instruction saying to lift the chair, move the chair and put it down, it basically picks up the chair and moves it down, right? So this is an amazing work from the Stanford group. You can check this out paper. This is a really great work on basically how do you control the interaction generation given a text description. Well, till now I have only talked about perception, right? So from a vision perspective, but I also hinted that we would not talk about like from vision to robotics, and I will tease you towards that, like what does robotics mean, right? Because all of this task that we are seeing now is solving a graphics problem, right? So it's basically solving a perception problem. So given an image or given a text, we are basically generating some kind of interaction basically that shapes you in that. But can it really help us in a real world, right? So if you remember that the initial video that I showed you about this Ex Machina, where there's a robot that moves in the real world, but these are virtual characters, right? So these do not really move in the real world. And I will tease you with this work from Berkeley, which is like an amazing work on this, right? And we are going towards it. like does 3D human perception help in robotics, right? And what we see is a paper called Video Mimic. What it does is like given an in the wild video, what we do is like you estimate the 3D body and the scene, right? And we basically retarget that to a robot. Like this was a G1 robot, I think, which is also very common now. By the way, these are super expensive. Not super expensive. These are very cheap, like $15,000 compared to earlier models of robots, which were like up in 100K dollars. So what you can do is you can get an in the wild video, and this is the task that we have been talking about now, right? Like perceiving humans in the wild, right? So there's a 3D perception of humans and the scenes. We can take this perception, we can basically retarget it using a robot and basically train a robot in simulation, right? And what it ends up doing is that the better your human perception is, the better the robotics would be. And this is a video from the web page. This robot is basically works, and the cool part about the robot is that it can basically walk in autonomously on various terrains. So it still cannot do a left and right, right? So it's still like somebody needs to control it where to move, but nobody controls it how to move up a chair, right? So it is all based and grounded in the fact that we are doing a better job of 3D human perception, right? And 3D scene reconstruction. So the better that is, because what you have ended up seeing is that the RL-based robotics have really not progressed over these years. Um, and this is very difficult because the in simulation work and the in the wild it really doesn't work. And what people ended up doing is that they took the route of 3D human perception, right? Understanding how humans move in a 3D. As you can see, a 3D human perception like a model, basically, your human moves it. You basically estimate how the humans move in a 3D world, retarget it to the robot, and basically make it move in the world. So now the main idea about that is that all the work that has been gone in understanding through human perception would ultimately bring us a robot that would help us in moving our task, right? So imagine a world where you ask a robot to pick up a glass of water, and the better the 3D human understanding model is, the better that is, right? And we are moving in parallel with robotics group, right? So we are building better and better human perception model, and robotics is basically bridging the gap from robotics to vision. Okay, that brings me to the summary of this talk, and I'm summarizing in a way that 3D or 4D human perception, like 3D plus time, is a key to solving the long-standing problem of AI, like building a realistic humans that look and act like us. Because reasoning like us has already been done by LLM, but it doesn't look like a human, it doesn't act like a human, and 3D human and 4D perception is a really way forward. Getting good quality data will always be challenging because humans interact with many different objects. It's not very easy to collect, and unlike traditional vision problems, it is very difficult to collect data in the wild. And some kind of a foundational model can help, like anything that do understand about the world. And the main trick would be like, how do you leverage this, right? Like, well, there is so much knowledge in ChatGPT, but how do you can distill that knowledge from this foundational model to solving a 3D task, right? Which they are not natively good at. They do have some understanding of the world, but not necessarily. So you can always say that this video diffusion model, they do understand physics, but not really so, right? Because if you put them in a physics simulator, it doesn't really work. And this is again my strong belief that the vision-led robotics is going to be important in coming years, because if you see vision, right? So I believe that AI is supposed to do two things, right? Answer the questions and do something. Anything apart from that is a temporary task, right? So if you think about image classification, image segmentation, these are temporary tasks that we created to move the field forward, because this doesn't have any ultimate goal, right? And for the first time, we are seeing a real application of vision in the real world. Well, we can always argue that, well, surveillance is a way to do, but actually that makes things work, right? So imagine that you have elderly care and you want to help, you want your robot to help you in cooking. So real application of the world will be led by vision and robotics, and I think this is going to be a very important field in coming future. And with all, thank you so much for listening. This is my email. You can note it down. If you have any questions, you can ping me. If you want to know about more work, because I gave a glimpse about some of my work, so there are more work, recent works that are there. You can visit my website on that. Thank you so much.
Yeah, so thank you, Sai, for your wonderful talk on 3D perception. So probably participants have got a lot of information on this recent topic.
Yes.
How difficult 3D reconstruction is, the way he has shown us the outputs. Probably it is difficult to get those outputs, as we all know. So, okay, participants, so if you're having any queries, so you can write it in the chat box. So that, all right. So, okay, let's wait, Sai, for a few minutes. Maybe they are typing, right?
Okay, sure. I'll just share my screen just so that. Okay. Okay. I'd also be interested to know if anybody is working on human perception. I'd also be
Yeah,
really cool to catch up.
very few in India, you know, that are
Yeah.
trying to solve this kind of problem because of its complexity itself.
Yeah, I
So
mean, this is really difficult in the sense that, yeah, I mean, it requires a lot of compute, a lot of data. Like so we have in our lab, we have this Hollywood studio where we capture data, and it's very expensive that way. Okay.
okay, let us check whether there are any queries. Yeah, there is one query in the chat box. What lightweight architectures balance performance and efficiency for real-time human-robot collaboration?
Yeah, that's a great question. I think yeah, we are not there yet. So, for example, the method that I talked about earlier is basically a contact prediction, which is basically a very important part of robotics. And we are still using a Lava model, which is like 25 GB. It runs in like 1 FPS and 2 FPS. It's not really great. There are recent works on that, like video LLM, video 3D LLM, which are running very low power vision tasks on reasoning part. But the locomotion part is still really difficult, right? So you can wear a glasses or some kind of a camera, which basically can reason about it. And you see a lot of papers from Apple, even from Meta, that doing on that task. But some sort of collaboration on 3D like locomotion, robot locomotion, and vision, there we are not there yet. But I think it should be okay. It should be there in a couple of years for sure.
Yeah.
And just to add on to that, that the way that we're using vision now is that traditional way of training these robots have been using RL, right? So you kind of put them in a simulator and that, right? And that has not really worked. And what people are not doing is that they're using this vision-led data curation. So they use vision model to basically collect the data for the robotics and use that to train a robot in simulation. And that's the collaboration that is going on now with vision and robots.
Yeah, there's another query.
Yes. Okay, I can also read. Is there any work on prediction next pose in the future? Yes. There are tons of work on predicting the next pose in the prediction. So there is something called TMR, which basically does a pose prediction. There is something called humor, which is again from our group. So what they do is given a keyframe, they predict the next frame. And yes, it's a very well-known problem in the literature, and you would find tons of work on that. You can check out humor that it can come up right from my head, but I think that is probably a couple of years back. I don't remember anything from this recent 1 or 2 years.
Yeah.
By the way, if you have any questions, you can always write on my email. You can shoot me an email. I'll happy to reply if nothing comes to your mind now. Can gesture-based post-production facilitate more natural communication with? Yes. Yes. So gesture-based post-production, yes, it helps us in more defining more realistic robot-like manipulation. But the most important problem in a gesture-based recognition is predicting the hand, right? So hands are really tough for us because like when you take a picture, you have an entire body and fingers compose a very less number of pixels in a camera, right? And because of this low quality, low pixel space in the image, it is very difficult to do good human like perception. And if you see the amount of degree of freedom that you have for fingers, it is a lot more. And so we don't have a very accurate method that can do very good hand prediction and body prediction. So we have models that can do very good hand prediction, and we have models that can do very good body prediction, and nothing that combines together. And yes, so once we can solve that in a very low resolution image, that can definitely help. And also from a robotics point of view, I talked to a few of my friends in Stanford. What they are saying is that we don't even know what kind of dexterity we need in robots, right? For example, we have 5 fingers, but we're sure that is 5 fingers really necessary for a robot to do it. So if you want to make like a human-like robot, like for example, if you want to deploy the robot in a elderly care, you definitely want them to look like a human, right? Because well, it creates some kind of bonding. But for example, the industrial robots, right? Do they really need 5 fingers? Because if you are able to do with 2 fingers, do you test that, right? So there is also still is an open problem from robotic side saying how many fingers do you need to do a better gesture part.
Yeah. I think that was the last query. Participants, if you are having any query, you can directly drop an email, right, to him.
Okay.
So email IDs are already, you might have also noted down.
Okay.
So he will definitely reply you back, right?
Okay. Yeah. Sure.
So thank you, Sai, once again for
Thank you so much
request.
for.
Yeah.
Yeah, I mean, thank you so much for inviting. This was a wonderful, place to talk, and also like to give a notion of perception, which is again, as we discussed also earlier, has not very widely been worked on in India. So I think it's really really nice.
Yeah. So thank you once again, right, on behalf of Computer Science and Department and E&ICT Academy at MNIT Jaipur. So I'd like to thank you for accepting our request and delivering your insightful talk on a very recent topic of computer vision. Thank you very much for joining us.
Thank you so much. Thank you. Bye.
Bye. Yeah. So participants will be having our next session at 6:20 p.m. That will be delivered by Professor Badri N. Subudi from IIT Jammu. So he'll be talking on activity recognition using deep learning algorithms. That is also one of the important